Let's get started going over some definitions and notation. The very first thing that Euclid writes in Book 1 as definitions is a point is that which has no part. Alright, so we have points. We'll usually represent them on the plane, and we'll define plane in just a moment, don't worry. But we'll define them on the plane with a single little dot. We will call this, well, we could put a P there, we could call this point P. We're not going to reserve ourselves to just calling points point P. We can call it point A, point B, point theta, point alpha, whatever you like. There's a point, we have something we can call it, point P. Notation-wise, you can just refer to this as P, or whatever we actually ended up calling it. Alright, so we have points, and a collection of points makes a line. Let's say we have a point A, and we have a point B. AB can form a line. This could be referred to as line AB. Written with our notation, AB with a line above it. Alright, line AB goes on in both directions infinitely. We'll go over that in a little bit more detail in a second. But for now, let's talk about some of the different ways we can see lines. Alright, different ways to break them down. The first way is that we could just have something called a line segment, which is simply, if we have point A and point B, the line segment is just these 2 points and everything in between them, but nothing beyond B and nothing beyond A in either direction. So just these collection of points here. We would call this line segment AB. And to denote it, we would write AB with a line above it. No arrows denoting that it's just a segment. Alright, so we have lines, line segments. Lines are made up of points. Number 4, rays. Well, if we have a segment and we have a line, then what if we just had the collection, the set of all points such that it's A through B and onward and upward to infinity? We would call this ray AB, or written AB with a line pointing in one direction above it. And so all this means is that A is part of this set, B is part of this set, everything in between them is a part of it, and everything beyond B is also a part of it. However, there's nothing over here. Alright, this ray does not have anything in this direction. We could create a ray, let's call it CD, that does go in this direction. Alright, and then we could call this ray CD, and since it's going in that direction, well, it's up to you. I don't really mind. You could call it ray CD, and you could try to distinguish that it's going in that direction. You could just as easily write it as ray CD. Okay? Direction and orientation don't necessarily matter, but if you want to distinguish it for yourself in your notation as you have it adjacent to your diagrams, go ahead. Whatever helps. Okay, so points, lines, and different ways to see lines. If a line is just a collection of points, then what is a collection of lines? Well, we will define a collection of lines as a plane. So you can imagine for a second that we have a single line, and that if we continue to extrude this line outward in this direction towards me, that we will end up with a plane. A plane is a surface on which we do our work. In fact, this entire board that I'm writing on right now, if you have a piece of paper and a pencil in front of you, you could define that as your plane. Planes can have points in them as well, of course, because, well, a plane is made up of lines and the line is made up of points. So, a plane contains points. We could call this plane here plane ABC. Alright. You okay with that? Good. Let's talk about angles. Let's say we have two lines that are not the same line, and they fall upon each other. And I am going to distinguish that these are lines, not line segments, by putting little arrows here. Call this point A, call this point B, C, D, and the point where they intersect, I'm going to call them E. All right? Euclid writes the following. A plane angle is the inclination to one another of two lines in a plane which meet one another and do not lie in a straight line. All that means is that if we have two lines that intersect and they're not a straight line, well, if they were both, that would mean they were both the same line. But two lines are intersecting, we have an angle right here. We can denote that angle in a couple of ways. The first way is angle. Use this symbol here, which represents angle. A, E, B. Okay? Angle A, E, B. There's another way to refer to this angle here. We could also refer to this as angle BEA. Okay? It's the same angle. In fact, we could write that angle AEB is equal to angle BEA. All right? We will get into a little discussion about congruency versus equality in a little moment. In this particular circumstance, these are the same exact angle. They are equal. Okay? All right. So we denote angle with this, and this is angle AEB. Let's see if we can write angle AED. Well, that's this angle here, which I'll denote with two lines on here. So I'll call this one angle AED. Can you see the other way to write angle AED? Well, that would be angle DEA. All right, and then we have some other angles here. We have angle DEC and angle BEC. That's the collection of all the angles that we have here. So angles exist, we can denote them, and we can refer to them. Okay. There are a few other things to mention. The first, let's take a look at the different types of angles we can have. Okay? First, let's say that we have a line. And I'm going to call this line A. I'm just going to call this line B. If line A and B meet such that they are perpendicular to one another, that is, that this angle here is equal to this angle here, then we have something called a right angle. You're used to seeing right angles as being denoted as 90 degrees. Okay? We're not going to be dealing with degrees for quite a little while. I mean, we'll get there. But for right now, all we're saying is that we have right angles. Okay? Such that, and this is how Euclid puts it, when a straight line set up on a straight line makes the adjacent angles equal to one another, each of the equal angles is right, and the straight line on the other is called a perpendicular to that on which it stands. Okay? So we have right angles. Next, we have obtuse angles, and we have acute angles. An obtuse angle is an angle that is greater than a right angle. So, in this diagram I've drawn here, angle AEB would be called obtuse. Why? Well, as we can see here, take this angle measurement, all right? Without even doing any measurements or anything, it is obvious just by looking at this, that angle AEB is greater than a right angle. It's far larger than this. If you cut it in half, these are both equal. All right. This here is an obtuse angle. It's greater than 90 degrees. All right. If you want to think about it for a moment in terms of degrees, if that's what you're familiar with, go ahead. We're going to be moving away from that. But for now, it's greater than 90 degrees or it's greater than a right angle. Likewise, this angle over here, angle AED, is acute, which simply means that it is less than a right angle. Okay. So, without any other thing to mention, if there's anything else that comes up as we go forward, we'll go through it and we'll define it then. For now, this will do. These are the words, these are the definitions and notations we are going to use. Thank you very much.